Perfect. You can start. Thank you.
Okay, thank you very much. Okay, first of all, I would like to thank all the organizer for organizing this event, and in particular Antonio for inviting me here. So I will, during this presentation, I will present the latest advance in quantum nanoplasmonic. In particular, in the first part of this talk, I will present the classical theory of surface plasmon polariton and localized surface plasmon. In second part of this presentation, I will show how very qualitative you can quantize this kind of excitation at nanoscale, and I will show some application. Okay, first of all, I would like to thank all my collaborators. And then let's start from a quick introduction in nanotechnology. Nanotechnology is actually a very old thing. I mean, a lot of ancient civilization knew how to actually use very small particle or nanoparticle to make a very, very nice piece of art. So for instance, Romans or actually Italians during the Renaissance or French people during even the Middle Age. They were able to use gold or silver nanoparticle inside different materials in order to make these kind of piece of arts very, very bright, very beautiful. But the main advance technology started from the second half of last century, thanks to the introduction of many technology that allow us to view things at nanoscale and to fabricate things at nanoscale. So here you can see some examples of microscope, especially the scanning tunneling microscopy or STM that allow us to see things at nanoscale, very, very small, and many other technology that allow us to fabricate things at nanoscale. Here I show just one example, which is the electron beam lithography that allow us to write down things that on the scale of 10 nanometers or even less. Okay, so once we know how to see things at nanoscale and how to fabricate things at nanoscale, next question is how can we use this technology to do things, and in particular to control electromagnetic field at nanoscale. Okay, so in principle, we want to use this small object to control the flow of light at nanoscale. How can we do it? So there are many ways to do it that have been proposed in the last years, and in particular, one possibility is to use small metal nanoparticles. Why? Because these particles, as we will see in the next slides and during this presentation, may resonate at nanoscale. Okay, so they will show an enhanced response at nanoscale that allow us to use them as building block of larger structure that allow us to control and manipulate light at nanoscale, in particular to, as you can see in this slide, you see very large structure in which the single bricks that make it, I mean the single building blocks, are made by very small nanoparticle that allow us to control waves, focus them, engineer the phase retardation, deflect the beam. These structures are called metasurfaces or metalens. Okay, and are very there are a lot of excitement in the community on this technology. Okay, so in order to understand the behavior of light at nanoscale, I will show you in a very, hopefully very simple way, two excitation that we can have at nanoscale. The first of them is the surface plasmon polarity. The second of them will be the localized surface plasma. Okay, let's start from the first one. And then in the second part of this presentation, I will introduce a way to quantize this excitation, still in a very qualitative way because the time is very short. Okay, first of all, let's talk about the surface plasmon polarity at a single interface between a metal and a dielectric semi-infinite space. Okay, so in this case, the space is divided into two parts. We have the first part, which is made by dielectric, that we can assume non-dispersive. So the permittivity of this material does not depend on frequency. And then we have the other part, which is made by metal. So this means that the permittivity of the bottom part can assume negative values, negative real part of permittivities. Okay, so in this case, we have to solve the Maxwell's equation, to find a non-trivial solution of them. And in particular, we look for transverse magnetic solution of the Maxwell's equation, full wave Maxwell's equation. Okay, in this case, we write down the Maxwell's equation in both medium, both equations, and in particular, assuming that the magnetic field is transverse, so Tm, we can do some simplification on this equation. At this point, we end up with this set of equations that can be combined in order to build the Helmholtz equation. Okay, we can apply the Helmholtz equation in both the space, so here and here, and then we assume we make an ansatz, we make an assumption that the electromagnetic field has this form. As I stated before, this is a Tm solution. So the magnetic field is only transverse with respect to the direction of propagation, which in this case is assumed to be x. Okay, x is the direction that we will see will be the direction along with the surface Planck polarity will propagate, and then we are assuming that the magnetic field is only confined in the transverse direction with respect to it, so the YZ plane. Okay, so at this point we can combine, we can substitute actually these ansatz inside the Maxwell's equation that we have derived before. We end up, and in particular, we can substitute these ansatz into the Helmholtz equation that we derived before, and then we end up with these two relations between, the k vector and the propagation beta vector. At this point, the last thing that we have to do is to impose, the continuity of the tangential component of the electric field in this case, and then this returns us this relation which links the permittivity in the two regions with the k vector in the two regions. Okay, by combining these relations with the previous relation that relates the beta vector and the k vector, we end up with the dispersion relation of surface plasmon polarity, okay, which is this one that we can plot over here by using different dispersion relation taken from the literature, in particular from the measured data for the permittivity, and we end up with the following plot. This is of course, the dispersion plot in which you can see on the x-axis the wave vector, on the y-axis the frequency, and in particular, what the information that this tells you is that surface plasma cannot be excited by propagating photons, but needing to be in some way coupled. And in particular, during time, there have been proposed different way of excite them. So, for instance, the Otto configuration that you can see over here in this slide, or the Kretschmann configuration that you can see here. I don't have time to go in detail on this configuration, but you can ask me later for references. But on the other side, we have another important excitation, which is the localized surface plasmon resonance. In this case, it's very easy to derive by using simply the Laplace equation and the basic theory of electrostatic, this excitation. Okay, so let's see what happens if we have a very small sphere, very small compared to the exciting wavelength, and we look for a non-trivial solution of the electroquasistatic problem. In this case, we have to enforce the Laplace equation inside the sphere and outside the sphere. We are assuming that the sphere is very small compared to the wavelength. At this point, we impose the Laplace equation inside and outside, and we have to impose the boundary condition for the potential. In particular, we assume that the continuity of the potential at the surface of the sphere and the jump of the derivative, normal derivative of the electric potential, and the condition at infinity. At this point, by combining this equation and assuming a solution in terms of vector spherical, scalar spherical harmonics, we end up, making calculation, enforcing this, those conditions. I have all the calculation here if you want to see them later. We arrive at the expression of the polarizability, which is induced by an external exciting field in terms of the permittivity of the sphere and the permittivity of the outside medium. In particular, we can identify over here the polarizability of the sphere, which is this one, which is basically the factor that makes the induced dipole moment proportional to the exciting field. But the important thing is that we can see that this quantity, the denominator of the polarizability goes to zero, and then the polarizability for a special value of the permittivity of the sphere goes to infinity. Okay, this is actually in a very idealized model, but still this is important because this retards us a very important condition, which is called Froelich condition. And in particular, the Froelich condition tells us that when the permittivity of the sphere is equal to minus 2 times the permittivity of the external medium, then we get a resonance, and the polarizability becomes very high. And this is a very important result that people during many years have used to make a lot of application. First of all, first application. So we see that this resonance position depends on the medium on the external medium, on the medium outside the sphere. So this means that by looking at the position of the resonance, we can in some way sense what is outside the sphere. Okay, so we can make a sensor because this resonance is dependent on the external medium. Then, but when this condition is matched when, for instance, if the external medium is, for instance, air, so this condition is matched, is verified when the relative permittivity of the sphere is equal to minus 2. So when this condition is met, so for instance, let's look at dispersion relation of noble metals, and we will see that this condition is met for a sphere in the quasi-static approximation at 480 nanometers, and for a silver at 350 nanometers. Okay, so the sphere will look green, and the silver sphere will look actually violet. But what are the consequences of these resonances? We can have two consequences. One consequence in the far field and one consequence in the near field. So in the far field, we can look to the total, for instance, for instance, to the total scattered power. So we actually shine the particle with an exciting light, for instance, a laser. Then we can actually detect the power scattered by this sphere, this object. And what we can see is if we vary the frequency of the exciting light, we can see a resonant peak. Okay, and this is very important because we have seen that this peak shift with the exciting independence of the external permittivity of the external medium, so we can make a sensor by looking at the shift of this peak. Okay, this is a first application that use the far field, but we can also think of application that use the near field. So we have seen that the polarizability goes to infinity, so we expect an electric field which is very high in proximity of our nanoparticle, and in fact this is the case. This is just a sphere, and we see an enhancement of the field of 4 times with respect to the incident field. So we have very high local field, and we can use for a plethora of application for enhancing for instance, nonlinear processing, but as we will see later, also for enhancing quantum processes, but also to make photothermal theory by heating up things in proximity of the sphere. Okay. But these resonance can be tunable, and in particular, if we change the shape of nanoparticles, so not a sphere anymore, but an arbitrary shape, for instance, a rod, by changing the aspect ratio of this rod, it's possible to shift the resonance and so engineer the resonance position of the plasmon. But I mean, in going more deeply into the theory, so actually the plasmonic resonances can be associated to the eigenvalues of an integral operator that you can see over here. In particular, this is an electrostatic operator that associates the surface charge density to the electrostatic field it generates. By looking at the property of this operator, we can actually derive all the property of plasmon modes. Okay. And in particular, by using the modes of this operator, the eigenvector of that operator, is possible to actually represent the induced current density in terms of these modes. By doing that, we actually see, by doing this expansion, that this expansion has a zero in the denominator in correspondence of the plasmon resonance. So we can, in such a way, generalize the Frolic condition to any shape by looking at the eigenvalues and eigenvector of that operators. So those are some examples. Those are all the plasmonic mode of the first three plasmonic mode of a sphere. So in the first row, you see the dipole mode, second row, the quadrupole, then the octupole. Those are the eigenvector of that operator. These are the plasma mode of a disk, and this is the plasma. Those are the plasma modes of a rod. Okay, so but plasma mode can interfere. By looking at the interference of plasma mode, it's possible to have Fano resonance, which are basically asymmetric line shape in the scattering. And those are very important because Fano line shape are very narrow and can be used for make very sensitive sensors. And those Fano resonances, Platonian nanoparticle, nanostructure, are associated to the interference of plasma modes. So when you have a cancellation of total dipole moment. And you can also inverse design plasmonic nanoparticle by actually coupling electromagnetic solver to inverse formulation. Okay, so over here you can see different arrays of plasmonic object or different shapes that have been optimized to have very, very high field enhancement. Okay, so now we have introduced classically the plasmon, surface plasmon polariton and localized surface plasmon, which happens respectively at the interface between a metal and electric and in a small metal nanoparticles. Now we see in a very qualitative way how we can quantize them. This is very important because in the last few years, as for sure you have seen in this summer school, there is a lot of interest in quantum technology. And in particular, you have seen for sure from the news that many companies are actually participating to a race to build a quantum computer which has many qubits as possible. So so actually, plasmon technology wants to make part of this race, and in particular, we will see in these few slides how we can exploit plasmon nanoparticle and nanostructure in order to engineer quantum effect at nanoscale. So first of all, we have to introduce a formulation in order to quantize the plasmon excitation. Okay, There are different ways to actually approach the problem. First of all, the problem of quantization of the macroscopic electromagnetic field in non-dispersive and homogeneous dielectric, so a dielectric that covers all the space, is not a big problem. In fact, this has been solved in the 1948 in this paper that you can see over here. The problem that you have in quantization of the electromagnetic field arises when you have a dispersive object in a finite medium. So this is a way more difficult problem. I will try to show you what are the different approaches in the literature. So we have this first contribution of Glauber and Legstein, and they have proposed a quantization scheme that is able to attack the problem of quantization in finite electric, which is actually non-dispersive. So they tackle the problem of the fact that the object is finite size, but not the problem of dispersion. But to deal with dispersive dielectric, we have to attack the problem in another way, following the path opened by Hopfield. Why this contribution is important? Because Hopfield introduced a way to describe the medium, which is, for instance, associated to a plasmonic particle, to an array of harmonic oscillator. Okay, so this he describes the matter as an array of harmonic oscillator. All the approaches that are based on this idea have the name of Hopfield type scheme. But there are other approaches which are based on the introduction of noise operator that I will try to introduce very briefly. So, first slide is for the Hopfield type approach. So Hopfield introduced a set of harmonic oscillator in order to describe the polarization field which is in use in the matter. At this point, there is still a problem, which is the problem of describing the losses inside the plasmonic nanoparticle, and this problem was overcome by Atner and Barnett because they extended the Hopfield model in order to include the losses, and they do that by introducing another reservoir of continuous bosonic field, so another reservoir of harmonic oscillator. Okay, these approaches, they were later generalized, and in particular it was only introduced just one field by papers by Sipe and Philbin. They introduced just one field that was able to describe both the polarization and the losses, so just one field. So this is actually a pictorial introduction to the Hopfield model, in which we want to quantize the field which is associated to this particle, and in particular we introduce a matter field which is associated to this particle, and is described with it's like a continuum of harmonic oscillator. And then this field has to be coupled with the electromagnetic field outside, in the whole space. And so we have the matter field, we have the field which is associated to electromagnetic field, and we have the coupling between them. Okay, so this is actually the Hopfield model, and all the subsequent approaches are based on this idea. On the other side, we have the so-called Langevin noise scheme. In this scheme for the quantization of electromagnetic field in nanostructure, there is the introduction of phenomenological fluctuation currents that deal with the problem of dissipation of dispersion. And in particular, in this case, all the electromagnetic field are expressed in terms of this noise current operator through the classical Green function. So at the end, in order to describe quantum mechanically the problem, at the end we have to know the classical Green function. Okay, we have to compute the classical Green function. These two approaches, so the Hopfield approach and the Langevin noise scheme, are basically equivalent, and these have been proved in the literature. Okay, at this point that we have a brief overview on how to attack the problem from a theoretical point of view, I will show you some practical contribution. And in particular, so actually in this paper, so this is 20 years ago, um, it, for the first time, we have the observation of a quantum effect in plasmonic nanostructure, and in particular in this paper, the authors actually had an array of gold holes. Actually, it was a grating of holes. Then they actually excited it with entangled photons. So these entangled photons were converted into plasmon and then outcoupled again to photons. What they have seen, and then at the end they were able to retrieve the entanglement between photons. Okay, so the plasmon preserved this entanglement. This was a very interesting result that is summarized in this paper. Then in this other paper by Giuliano Di Martino and other, so authors actually, they were able to excite, with a photon, a single plasmon that propagated along a plasmon waveguide and was outcoupled. So this is very important because show that we, as a scientific community, were able to actually manipulate a single plasmons. Okay, but the important thing,
Carlo, you have 5 minutes. Okay.
All right, yeah, I will make. Okay, so the important application is in the coupling between plasmon and emitters. Okay, so in particular, the spontaneous emission is a process in which a quantum mechanical system transits from an excited energy state to a lower energy state, and we have an emission of photon. So this includes luminescence, fluorescence, and phosphorescence. Okay, they are different shades of the same effect. And in particular, a single emitter can be used as a discrete source for quantum communication information processing. So it's very important to enhance and in particular control their emission. The important thing is that there is a large size mismatch between light and single emitter, and we have in some way to use, for instance, plasmon nanostructure in order to enhance the light matter interaction. Okay, and this is shown in this slide. And in particular, the nanoparticle, the plasma nanoparticle, can be a bridge, okay, to actually tackle this size mismatch. So there are two possible regimes of interaction between this emitter and the plasma nanoparticle, which are the strong and weak coupling. Now I will try to introduce this difference by a simple classical analogy in which we have two harmonic oscillators which are in some way coupled between them, which is with a coupling constant. Now, they are described by these two classical equations, which are coupled by this parameter k. So we can make this actually conceptual experiment if we take fixed the first value of k, so the first spring constant, and then we vary the second spring constant. Okay, so if we do that, so when the two oscillators are uncoupled, so we have that the first spring constant, the first spring constant is constant, and so that will be constant the frequency resonance of the first oscillator, while the second will vary because we are varying on the x-axis the spring constant. But if we introduce the coupling, so what we will see will be an anti-crossing between the two resonant frequency, and this is actually a signature of the condition of strong coupling, this anti-crossing. But the problem is that so far we didn't introduce damping. If we can introduce damping, then it's possible that if the damping is very high, we will not able to see anymore this anti-crossing. And in this case, the definition is that we will be in the weak coupling regime. But if the coupling is stronger than the damping constant, so the damping, so we will be able to see this anti-crossing, and then we will be in a strong coupling regime. Okay, so the weak coupling regime is very okay, and here you can see a different structure in which you can be either in the weak coupling regime or in the strong coupling regime. Okay, the weak coupling regime is very important because it's dominated by the Parcel analysis, Parcel factor, because Parcel 70 years ago actually predicted that the spontaneous transition rate of an emitter can be modified by the environment. Okay, so what is telling us that we can use a nanostructure in order to engineer the emission rate of an emitter. Okay, and this can be actually calculated, this emission rate, by calculating the classical Green function of the system. And here you can see some experiment in which actually the emitter is coupled to a plasmon here. This is basically a wire, a plasmon wire, and the emission is enhanced, and the state is preserved. On the other side, it has been recently demonstrated also a strong coupling between a emitter and a gold nanoparticle, and in particular this has been done at room temperature thanks to the gap plasmon between a plasmon, a nanoparticle, and a gold substrate. Okay, this is a particle on a mirror substrate and configuration. And in fact, actually you can see the splitting of the two resonance, which is due to the strong coupling between the particle and the emitter. This is called Rabi splitting, and is actually signature of the condition of strong coupling. Okay, so this is brings me basically to the conclusion. So what we have shown, I try to introduce to you the physics of localized surface plasmon and surface plasmon polariton, a brief overview on how to quantize it, very qualitative because there is no time, and some application to the single plasmon control, and to the use of the coupling between single emitter and plasmon to realize weak or strong coupling. And with this, I thank you for your attention.